Hey, hello there. So today I'm looking at two more bit manipulation questions. Since they are similar, so I group them together. They are similar in the sense of the usage of bit mask to help us to enumerate over a range of possible scenarios. So these two questions are 784, letter case permutation, and the 78 subsets. So we're actually going to start with 78 because it's actually easier, even though the difficulty level is marked as medium. So we have a set of distinct integers, nums. We need to return all the possible subsets, and we should exclude the duplicates. So basically every element in this example, if we look at this example with three elements, they have a choice to whether to present or not present in a certain realization of the subset. So that's every location have two choices. We have three locations, so that's 2 to the third. We get 8 different possibilities, and that's exactly how many subset we generated here. So we have the empty set, which every element choose all to present, and we have the single element subset. Only one of the elements decide to present, the other two not. We have the two element subsets, 3 of those, and the full set with every element decide to present in this subset. So that's 2 to the third different subsets, and every subset, even though this only have one number in there, it's actually 3 different choices made up to that. And we can actually use a 3-bit unsigned integer to represent this subset, where just take example, the first location from the left is going to present encode whether this one will be present in this subset or not. Similarly, we have the following location for 2 and 3. The empty set basically corresponds to 0, 0, 0. A single element set like 2 here will can be encoded as 0, 1, 0, and the 2 element set similarly like 1, 3 will be 1, 0, 1, and of course the full set will be 1, 1, 1. So that's pretty much the relationship between each subset and the binary number representation. So how many numbers we need to represent all of those? We have 2 to the 8, 2 to the third, so we actually just need a number from 0 to that, with the 8 largest number be exclusive. So we can have up to 2 to the third minus 1. So that's 1, 1, 1 in binary. So to enumerate over all the possible combinations, we just need to grab this number from 0 to 7 inclusive, 7, 8 exclusive, and look up the binary representation for the number, and look at the 1 bits to put the number inside the set. We can effectively generate all those subsets without any duplication, and very effectively, I think. So that's pretty much the big idea behind this question. If we choose to use this bit mask kind of formula, so let's solve this. So the first thing first is that we want to find this upper bound. This upper bound is defined by 2 to the number of elements in this number. So let's just very quickly grab this. And then we initialize the placeholder for the result. And just gonna enumerate over these possible ranges. So it's we should be less than 2 to the number of elements. So that is equivalent to say shift 1 bit towards left by a this amount, and then what we should do is to just increment the mask for each iteration. And this mask in the binary representation will tell us the which element we should pick and throw that to form a subset. So we're going to have a subset, which is a vector of integer numbers. And then we're just going to, in this mask from bit to bit, we're going to, if it's a 1 bit, we're going to put the number that's, the ice number, just going to put that into the subset. So if this mask, and we shift a 1 bit towards left by this amount, if that turns out to be a 1, that means this i's number from nums in this particular subset is present. So we push the element onto the back of this vector. And that's pretty much how we construct a subset. So for every element in nums, we're gonna try to figure out, look up, is it existed in this specific subset? If it's indeed in there, we push it onto this subset. And after we generated the subset, we're just going to put that onto the results. And that's pretty much it. Yeah, so this is a demonstration about how we can actually use a range of integer numbers to represent the choices. And it's important to see that every element has a correspondent bit position, and every element has exactly 2 kind of options, whether to present or not present. So that's why they can be modeled by the 0 and 1 in this number range in their binary representations. So that's 78. And then is 784 letter case permutation. What we have is an input string. We need to transform every letter individually to be lowercase or uppercase to create another string. And we need to return all the possible strings we would create. So as an example, we have A1, B2. So the digits don't have lowercase and uppercase kind of distinction. So all we need to do is to try to come up with all the possible upper and lowercase combinations among the alphabet, English characters. So we can have lower a, lower b, lower a, upper b, upper a, lower b, and upper a, upper b. So basically for all the English letters, they have 2 choices, whether they can be in the lowercase or they can be uppercase in a specific realization of this transformation. And that's exactly similar to this, whether we present or not present in a subset, a realization of the subset of this full set. So that's why we can use a bit mask to encode that kind of, to enumerate over all the possibilities. So it's actually slightly difficult compared to this one, because this always deal with integer numbers, but here we have characters and digits that sort of mingle together. So yeah, so that's why this, even though this is easy, it's actually a little bit harder than 78. So yeah, so the strategy is basically to first find how many letters we have in the input string, and create a bit mask to enumerate over all the possible upper and lower case with that amount of English letters. Then we're gonna enumerate over all the possible upper and lower case situations. For each one of them, we're just gonna construct this, and that's pretty much the strategy. So the first thing first, we need to find out exactly how many English letters are there. That would be our upper bound for this bit mask number range. So what we're gonna do is to do an accumulation. Let's just call this n to be 0. For character in the string, we're gonna increment the count if the character is a alphabet. This will return a positive integer if it's a real alphabet. If it's not an alphabet, it will be exactly 0. So if we test it whether it's possible, it's a positive, then it will be, if you evaluate to 1, so we can increment n by this. So that's this for loop to come up with the count of English letters, and then we're gonna create a placeholder to store all the possible strings. And we're just gonna enumerate over all the possible bit masks. Similarly, it's by shifting the upper bound is 1 shifted towards left by this total number of elements, and it's a exclusive bound. For here, we're just gonna create an empty string and enumerate over all the characters by character, and we need to keep track of whether we are looking at the first. If we are looking at the digits, we directly put it onto the string, append it to the back of the string. If it's English letters, we need to look up the mask to find if it's in there. So we have to keep track of this is the inside the for loop here, whether it's I'm just gonna code this, have the next second loop here. Inside the second loop, we need to keep track of which the current character. If it is a English letter, it's the i's, whether it's the first or second that we encounter. That's because that number will be the number that we look at in the bit mask to tell us whether this should be uppercase or lowercase. So what we do is, if the character is not English letters, then we're just gonna push the character to the back of the string. Otherwise, we have two things to do. First thing was because the next iteration when we see a English letter, it will be the second, third, so we have to increment this count. The other thing is to look up in the mask. It will be the same formula as in the previous lookup. It's mask, and by shifting it 1 bit towards left by the i's location, by i's position. If this is true, it's telling us we should let's just make a simple decision. If it's a 1, it's uppercase. If it's a 0, it's lowercase. So we definitely need to push something onto there. So if the condition is true, we push a uppercase to upper. Is that this? Otherwise, it's to lower. And after this, nested loop, we populated a realization of the permutation. It's called permutation. Weird. And then we just push it onto the result. So that's the this problem. Nope. Oh, okay. I should increment mask. And what else? Yeah, it's working. So yeah, so this is the second question, letter case permutation. It's marked as easy. It's really not. If you choose not to do the bit mask as the this kind of lookup to sort of like a smarter way to come up with all the possibilities, you would potentially just do DFS. So for whenever you see a English letters, you're just gonna try different, have two DFS calls, and yeah, so it's definitely not an easy level question. So in terms of this time and space analysis for all these two questions, since that they are generating all the possibilities, it's the number of choices, 2 to the number of choices multiplied by the length of the string for this one, and they will be multiplied by the number of elements in this. Yeah, so it's n multiplied by 2 to the n in time and space. The space, if you consider the output. If you don't consider that's part of the space, then what you can see here is this basically just an integer number, and everything else gonna be it belongs to the output. So if you exclude outputs, then this is just a binary integer number as the mask. It's a similar story for this. All the strings that use spaces are part of the result, and the helper, the auxiliary kind of space are just this mask. Yeah, so so that's these two questions utilizing the bit mask to help us to go through all the possibilities. So the string, the code is actually quite nice, much cleaner than if you have to hand code the 0, 1 at every position. So yeah, so that's this smart use of bit masks. That's the question for today.